My Gavanin folks. Today we're going to solve all the integrals from the 2025 MIT Integration B finals. Problem 1 is the scary looking antiderivative problem involving trig functions and nested square roots. Okay, cool. To solve it, we'll make use of an interesting transformation here, and that is taking this term, 4 plus cosine x, and setting this equal to u squared. The reason for that being, 1, we get rid of one of the square roots, and 2, trig functions are quite nicely related to each other in terms of differentiation and integration. What do I mean by that? Well, differentiating this gives us minus sine x, terribly sorry about that, dx equal to 2u du, which implies that dx is just minus 2u du over sine x. Now, I could express sine x in terms of the u variable, but we have a tangent term here, which we know is sine x over cosine x, which means we have some nice cancellation taking place. So this implies that I here is now negative 2 times the integral of tangent being sine x over cosine x times the square root term, which is 2 plus root u squared, which is u. And then we have u times du over sine x, the cancellation I was talking about. And we have minus 2 times the integral of u times root u plus 2 over cosine x, which recall should be, well, u squared minus 4. So we have u squared minus 4, which does indeed have a nice factorization. That is u minus 2 times u plus 2, which is good because we have root u plus 2 upstairs and u plus 2 downstairs. So that gives us 1 over root u plus 2. So I is now minus 2 times the integral of u du over u minus 2 times root u plus 2. Okay, cool. Now the new integral looks a lot friendlier relative to the integral we started off with anyway. And to solve this thing, we'll start off by expanding by 0. And what special form of 0 do I need here? Well, let's say we'll make use of minus 2 plus 2. Why exactly? Well, obviously for more cancellations. So invoking the linearity of the integration operator, we have negative 2 times the integral of u minus 2 over u minus 2 again, root u plus 2 du, cancellation, minus 4 times the integral of du over u minus 2 times root u plus 2. So that leaves us with minus 2 times the integral of u plus 2 to the negative 1/2 du, which is pretty straightforward. That's just u plus 2 to the 1/2 over 1/2, and simplifying gives us minus 4 times root u plus 2 minus 4 times this fascinating looking integral, that is du over u minus 2 times root u plus 2. That we will solve using a transformation that, you guessed it, gets rid of the square root term. We'll let u plus 2 equal t squared, implying that du equals 2t dt. So our integral is now 2t, terribly sorry about that, dt over u, which is t squared minus 2 again, so that's a minus 4 downstairs, and we have t, cancellation, and we're left with a pretty straightforward integral to solve. That is integral twice the integral of dt over t squared minus 4, which I'm factorizing. And now we have an integral that's pretty easy to solve using partial fractions. So we have 2 times integral 1 over t minus 2 plus 1 over t plus 2. No, wait, the minus sign should work here. That way we have 4 up top. So to balance that out, I have to multiply by 1/4. And there you have it. We have 1/2 outside times a couple of straightforward integrals that can be solved using logarithms. So we have log absolute value t minus 2 minus log absolute value t plus 2, or using log properties, we have log absolute value t minus 2 over t plus 2. Okay, cool. recall that the target integral I was just, well, -4 times root u plus 2. And what exactly did we have? Yeah, a -4 over there. So -4 over 2, that's 2 times log absolute value. What exactly do we have? T minus 2 over t plus 2, but in terms of the u variable. So we actually let u plus 2 equal t squared. So t equals root u plus 2. So we have -4 times root u plus 2 minus 2 times log absolute value, u plus 2 minus 2, terribly sorry about that, over root u plus 2 plus 2. And now what exactly was the u variable? U was in fact root 4 plus cosine x. So we have this really awesome looking result in terms of trig functions and nested roots, just as expected. We have -4 times, well, root 2 plus root 4 plus cosine x. And we have a -2 logarithm absolute value root 2 plus root 4 times cosine x minus 2 over root 2 plus root 4 plus cosine x plus 2 plus a constant of integration, which is not required by the competition as far as I remember, but we're math nerds. I mean, why not? That was awesome. Now for problem 2. Problem 2 was definitely one of my favorites. Guys at MIT love the floor function. And we have integral 0 to infinity dx over x plus 1 plus floor of 2 root x whole thing squared. Okay, cool. So we'll let x squared equal u to get rid of the square root again. We're doing that quite a bit today. So this implies that, wait, I was supposed to let x equal u squared rather. Yeah, that makes sense. So dx equals 2u du. And the limits of integration are clearly not bothered. They're still going to be 0 to infinity. And we have 2u du over x, which is u squared, plus 1 plus floor of 2u whole thing squared. Now, how to deal with this floor function? Well, the output is going to be an integer. More specifically, for u belonging to the interval between n over 2 and n plus 1 over 2, we have 2u belonging to the interval from n to n plus 1, which implies that floor of 2u would equal n. Okay, cool. So all I need to do is take the integral operator and divide it into an infinite sum of integrals over intervals of length 1/2. So we start at 0 to 1/2 plus the integral from 1/2 to 1 plus the integral from 1 to 3/2 and so on and so forth. That is the sum over n from 0 to infinity of the integrals from n over 2 to n plus 1 over 2. And that's exactly what we need. So I equals the sum over n from 0 to infinity, integral n over 2 to n plus 1 over 2, 2u du over u squared plus 1 plus, we just saw what that floor of 2u equals. That would equal n. So that means we just have n and we're squaring the whole thing. So the integrals are pretty straightforward to evaluate. So we've basically turned this into an infinite series problem. So we have the sum over n from 0 to infinity of what exactly? Well, we're left with -1 over u squared plus 1 plus n, limits being, if I switch up the limits, I'm rid of the negative sign. So that's exactly what I'm going to do. We have lower limit now n plus 1 over 2, upper limit being n over 2. Simplifying or expanding gives us the sum of what exactly? We have n squared over 4 plus 1 plus n minus 1 over n plus 1 squared over 4 plus 1 plus n. Expanding by 4 gives us 4 times the sum over n from 0 to infinity of 1 over n squared plus 4n plus 4 minus 1 over n plus 1 squared plus 4n plus 4. Now all we need is some algebra. So for this thing here, we see that this is just n plus 2 whole thing squared, and that'll come in handy because we have the sum over n from 0 to infinity, so immediately we think of the Basel identity. And what about this bad boy here? This is n squared plus 2n plus 1 plus 4n plus 4, which is n squared plus 6n plus 5, which can be easily factorized as n plus 5 times n plus 1. Okay, cool. Another partial fraction decomposition. N plus 1, n plus 5. Again, I need a n plus 1 here. Minus sign will suffice. But then I need a factor of 1 over 4. Okay, cool. So multiplying by a quarter here, and we're all set. So this implies that I here equals 4 times the sum over n from 0 to infinity of 1 over n plus 2 squared minus 4 over 4, so there's some cancellation there, sum over n from 0 to infinity of 1 over n plus 1, terribly sorry about that, minus 1 over n plus 5. So this thing over here, going from n to n plus 1, or n to n plus 2 that is, would just be the sum over n from 2 to infinity of 1 over n squared, which is just pi squared minus 6, pi squared over 6 minus the first term in the sum, that is 1 over 1 squared. So that's just pi squared over 6 minus 1. And this thing is obviously going to be a telescoping series. So let me just evaluate this thing separately. We'll call this thing S. So S would be equal to what exactly? So we're starting off with 0, so 1 over 1 minus 1 over 5 plus 1 over 2 minus 1 over 6. You guessed exactly what the answer is going to be, but I'm still going to evaluate it. 1 over 3, 1 over 7, and 1 quarter minus 1 over... Oh, terribly sorry, I forgot math, which is not the first time. 1 over 5, right? So that's going to be... No, it is 5. I am doing this correctly. I did not forget math. False alarm, folks. 1 over 5 minus 1 over 9, and I think that should be enough because you get the idea. We're losing this term. We're going to lose the 1 over 6 term next. Then we're going to lose the 1 over 7 term. So the only surviving terms here are 1 plus 1 half plus 1 third plus 1 quarter, which gives us... what does it give us? 12, I guess? Yeah, this is the part where I struggle. We have a 12, so we have a 12 plus a 6 plus a 4 plus a 3. Come on, you can do this. You can do this. 18. What's 18 plus 7? 25? Okay. I can do this. I can totally do this. Come on, man, you got this. You got this. Okay, so I here equals 4 times pi squared over 6 minus 1, which we know is going to be 2 pi squared over 3 minus 4 plus 25 over 12, which is 2 pi squared over 3 minus 48 plus 25, 73 over 12. Yeah, that agrees with the results from MIT. Nailed it. Problem 3 now. Yeah, not exactly a fan of problem 3. I mean, it's alright. Yeah, whatever. 1 plus root 5 over 2 is, of course, the golden ratio, phi. So we have integral 0 to 10, terribly sorry about that, phi to the floor of x dx. So we have a finite interval of integration, and this problem is relatively straightforward. We can express this as a sum over n from 0 to 9 of the integrals from n to n plus 1 of phi to the, you guessed it, n dx. Now phi to the n is just going to be a constant for each integration. So we have the sum over n from 0 to 9 of phi to the n integral n to n plus 1 dx, which is just an interval of length 1, gives us a 1. Okay, cool. So now we just have to sum up powers of phi. Now, powers of phi can be expressed in terms of linear, or can be reduced to linear powers of phi. Let me show you what I mean. Phi to the 0 is going to be 1. So floor of... Oh man, I forgot. I completely forgot. Sorry. Bloopers here live, folks. This is a floor function over here. Does that affect anything? No, because again, you have floor of phi to the n integration with respect to x. So yeah, it doesn't affect anything. Okay, phi is approximately 1.619. So 1.619. Doing approximations now. So like I said, every power of phi can be just reduced to, every integer power of phi can be reduced to a linear, reduced to the linear power. That is phi to the 1. So phi to the 0 is just 1. So you get a 1 here. Phi to the 1, the floor function of that would be 1 again. Now phi squared is just phi plus 1. So that's going to be 2.619. So this thing is 2. Now what's phi cubed? Oh, something that would come in handy. Phi squared equals phi plus 1. So multiplying by phi to the n minus 2 gives us phi to the n equal to phi to the n minus 1 plus phi to the n minus 2. Yeah, that's something nice to know. So phi cubed is just phi squared plus phi. And again, phi squared is just phi plus 1. So you got 2 phi plus 1. So this thing would be, what, 3.2 something plus 1 and a 4. And you can continue this on and on. Do I have an efficient way of calculating this? No, but the guys at MIT, I mean, those guys are smart. They're brilliant. They could do this. They could do this while they were asleep. So yeah, in this thing, just sum up all the numbers. You do get 193. Not the most fun problem in my opinion, but again, great for people a lot smarter than me. Now for problem 4. Now, problem 4 was the problem I struggled with the most. And a hint given by the presenter was that the max and min functions don't matter, which I tried to work out, but I just couldn't get the idea. So if you do, please comment down below. That would be awesome. We would have a much better solution than the solution I'm going to present over here. The max and min functions, what do they do? Well, max of f and g just returns, terribly sorry about that, whichever function is greater on the interval we're talking about. Okay, cool. And the min function would, of course, do the opposite. We have the max of trig functions in absolute values, and we want to square that, which is cool because f greater than g implies that f squared is going to be greater than g squared. So what I'll do is I'll just distribute the squares, and I can get rid of the absolute values as well. So I have integral 0 to pi max of 4 sine squared x 2 cosine 2x minus 1 squared times the minimum of sine squared 2x and cosine squared 3x dx. Now, we could get rid of the maximum and minimum functions here instead of drawing a bunch of graphs of the trig functions or solving their equations. Solving the equations for when the functions are equal. We could avoid all that by using the fact that the maximum of f and g equals 1/2 of f plus g plus absolute value of f minus g. And the min of f and g equals 1/2 of f plus g minus the absolute value of f minus g. I know that does not sound very comforting, but the key thing here is the absolute value. Now, if f minus g is positive, we get f minus g, but if f minus g is negative, we get negative of f minus g, which actually comes in clutch over here. But to compare the signs of the trig functions involved, well, the differences of the trig functions involved, it would be useful to get rid of the double angles and triple angles involved. So starting off with 2 cosine 2x minus 1, terribly sorry about that, 2 cosine 2x minus 1, what the hell am I doing? Okay, cool. So we have 2 cosine 2x minus 1 squared. Cosine 2x, we know what that thing is. That is 2 cosine square x minus 1. So we should have 4 cosine square x minus 2 minus 1, which is minus 3. Okay. We have the whole thing squared. And expanding this gives us 16 times, wait, I have a sine term there, so I might as well express this in terms of sine functions, I guess. Yeah, that would actually be cool. So, yeah, f plus g, f minus g, I do need sine functions. I would like sine functions. 2 minus 4 sine square x minus 1. So that is just 1 minus 4 sine square x. Okay, cool. So that is 16 times sine to the 4th power of x minus 8 times sine square x plus 1. Okay, so if I'm comparing f minus g over here, calling this f and calling g for sine square x, if I'm looking at f minus g would be 16 times sine to the 4th power of x minus 12 times sine square x plus 1. So the leading coefficient here would be 16, and we do have powers, even powers of sine x, so no negative numbers involved. Approximately, we see the picture. We get the idea that, terribly sorry about that, we get the idea that absolute value f minus g should be equal to f minus g because this thing is positive. Okay, cool. So for the max of, what was it? Oh yeah, 4 sine square x and 2 cosine 2x minus 1 square, I would have 1/2 of f plus g plus f minus g, which cancel out quite nicely, meaning that I have 2 times f, which is, of course, just equal to, well, 4 sine square x. Okay, cool. And a similar exercise for the minimum term, which of course involves a sine of 2x and cosine 3x. So quite a bit of trigonometric and algebraic expansion, but we will find that in that case the f minus g term is negative. So for the minimum of sine square x, sine square 2x, cosine square 3x, that is, this thing equals 1/2 of f plus g minus f minus g. So in this case, the f terms cancel out. And we're actually just left with, well, cosine 3x. And this implies that I here just equals the integral from 0 to pi of 4 times sine square. So we have the 4 outside. We have sine square x times cosine square 3x dx. Again, expansion of the cosine term, the cosine 3x term, and then some integration, preferably using special functions, the beta function, of course, will yield pi over 4. I'll leave that as a bit of homework to you. So we have 4 times pi over 4, which is, of course, pi. And that solves the most annoying integral on this year's finals. Now for the grand finale. We have quite an interesting integrand, and this integral actually involves a nice trick that I will get to later. The first thing to notice is what happens when we combine the first and third terms. So we have integral 0 to 1 minus 1 over 2x plus root. We got 4x squared down here, 1 plus 4x minus 4x cubed, and then we have this other term that's x to the 4th power minus 4x plus 4 over 4 dx. Okay, cool. Now this thing here is minus 1 plus root 1 plus 4x minus 4x cubed over 2x, and we'll actually call this thing y, not for a u substitution, but as the function y. This thing is invertible on our domain of integration, and we're going to find the inverse of this function. I know, sounds weird, but these kind of integrals do pop up in MIT's Integration Bee from time to time, and if you're looking for more problems of this sort, do check out my boy Daniel Rosato's channel. I'll link a video of his in the description box relating to integrals like these. His channel is pretty cool if you're into like competitive math or integration bees and that kind of stuff. So do give him a subscribe, and give me a subscribe as well. I mean, I do integration bees. Well, I've been doing them every year since... I've been doing the finals every year since 2023, and the reason for that was back in 2023, I saw that no one was covering the Integration Bee finals, so I thought, why the hell not? I mean, it was fun. I loved doing that, so I carried forward the same practice in 2024, and now today, 2025, here we are. Anyway, how exactly are we going to deal with this? So this thing is invertible on the interval from 0 to 1. And I'm trying to find an inverse function. So I'll expand by 2x. So we have 2xy. I'll also expand by a plus 1. So we have root 1 plus 4x minus 4x cubed on the right. I'll square the whole thing to yield 4x squared y squared plus 4xy plus 1. Equal to 1 plus 4x minus 4x cubed. What am I going to do now? I have no idea. I'll just take everything to the other side of the... I'll just take everything on the right to the left. Or I could just expand by 1 over 4x. So that gives me what exactly? Well, I've got lots of nice cancellations. And xy squared plus y equal to 1 minus x squared, which implies that we have x squared plus xy squared plus y minus 1 equal to 0, which is a quadratic equation in x. Solving this gives us x equal to, well, let's see, we got minus y squared plus or minus y to the 4th power, looks familiar, minus 4 times, well, we have a 1, and we're left with y minus 1. So we have 4y plus 1 over what exactly? Well, we have a factor of 2. Okay, cool. So we have f inverse of x equal to, wait, we still have to deal with the plus or minus signs. So f of x was defined as minus 1 plus root 1 minus 4x. No, wait, it was plus 4x minus 4x cubed over 2x. And we see that this thing is non-negative, rather it is in fact positive on the interval 0 to 1. Okay, cool. So this thing is positive on the interval from 0 to 1, which means what we need is we need the plus sign. So this implies that f inverse of x is just negative x squared over 2 plus root, terribly sorry about that, root x to the 4th power minus 4x plus 1 over 2. And this thing looks incredibly familiar, doesn't it? Let's just scroll up a bit and... oh, yes, indeed. We have exactly that term. So that means our target integral I equals the integral from 0 to 1 of a certain function of x plus the inverse function of x plus a factor or term of x squared over 2 dx. Okay, cool. Now, using the linearity of the integration operator, we have integral 0 to 1, x squared over 2, so that's a 1/2 outside, dx, plus the integral from 0 to 1 of f of x dx, plus the integral, rather, I'm missing something. There was a negative sign over here, so that means there should have been a... that whole thing with a negative, so we have minus sign here and minus sign over there. Okay, cool. Negative sign here, 0 to 1, f inverse of x dx. And what exactly are 0 and 1? Recall again the definition of f of x. And we need to consider a couple of limits here. As x approaches 0, we do get a 0 by 0 form, which you can verify by L'Hopital's rule. The limit evaluates to 1, so f of x approaches 1, and as x approaches 1, we have f of x approaching minus 1 plus 1 over 2, which is, of course, 0. Okay, cool. So we see a kind of switch up in limits. 0 here is f of 1, and 1 here is f of 0. So I could write this thing as negative 1/2 x cubed over 3. That's 1 over 6 with those limits. So we have negative 1 over 6 plus integral 0 to 1 f of x dx plus integral from f of 0, terribly sorry about that, to f of 1, f inverse of x dx. And now for a nice trick involving inverse functions and functions, that is. Now, I'll link Daniel's full video in the description box, but here's a brief overview of it. So we have an increasing function in the diagram. Our function, of course, is a decreasing one, but it works either way. All we need is some injective function. So this here is the point A on the x-axis, and this here is the point B on the x-axis. And of course, we have the corresponding f of a, and of course, we have the corresponding f of b. Terribly sorry about that. My art skills aren't exactly all that great. Anyway, so this is f of b. Okay, cool. So this area over here is, of course, you guessed it, the integral from a to b of f of x dx. But what if you were to draw a separate diagram for the inverse function, or you could just look at this diagram we have over here as well? What about this area over here? Yes, indeed, you guessed correct once again that this would be the integral from f of a to f of b of f inverse of x dx. Okay, awesome stuff. Now, what about this little area over here? Well, that's just a square that has an area of a times f of a. And if you add together all these three integrals, all these three areas, that is, we have the integral from a to b of f, plus the integral from f of a to f of b of f inverse, plus a times f of a, well, then you have a rectangle of area b times f of b, which is pretty awesome. So this implies that, let me just write this somewhere else, a times f of a, much better. So all of this implies that the integral from a to b of a function f plus the integral from f of a to f of b of f inverse equals b times f of a minus a times f of a, which is a very cool and quick geometric proof, of course, for an invertible continuous function. And we could write this as x times f of x, terribly sorry about that, with the limits being a and b. Okay, cool. So this implies that our target integral I is in fact negative 1 over 6, plus we have exactly what we needed. We have over here in yellow the sum of an integral plus its inverse, plus the integral of the inverse. And we're left with x times f of x evaluated at, well, 0 and 1. We just saw as x approaches 1, f of x approaches 0, and as x approaches 0, the whole thing collapses to 0 anyway. So we have the target integral I equal to negative 1 over 6, agreeing with the results from MIT. And that was awesome. Comment down below your favorite problem from this year's finals. I hope you enjoyed the video. Be sure to like and subscribe. Drop me a follow on Instagram as well, and thank you. See you next time.